By 1946, it was abundantly clear that the technical potential of the first-generation Soviet jet engines had reached its absolute limit. Building a truly modern, competitive tactical fighter around them was impossible. At the same time, the development of domestic high-performance engines was severely lagging. As a result, Soviet aviation leadership looked abroad for new technology. A special delegation was sent to Great Britain in late 1946, where they successfully purchased the latest turbojets from Rolls-Royce. These included the Nene, producing a then impressive 5,000 pounds of thrust, and the Derwent 5, putting out 3,500 pounds. Another critical advantage of the British engines was service life. They boasted a time between overhauls of 180 hours, while early Soviet engines could only manage a modest 25. Acquiring these engines gave a massive boost to the Soviet aviation industry. Leadership ordered the British Nenes and Derwents to be completely dismantled and reverse-engineered down to the last bolt. The goal was to study them and set up domestic mass production as quickly as possible. In the Soviet Union, these cloned engines received new designations. They became known as the RD-45 and the RD-500. Immediately after, the design bureaus were given a clear directive. They needed to develop entirely new experimental aircraft to take full advantage of these powerful new engines. This formally launched the massive development program for their second generation of tactical fighters. The new technical requirements were officially approved by the government on March 11, 1947. The targets were demanding. The new fighters had to reach speeds of around 540 knots, achieve a service ceiling of 42,600 feet, and carry at least three 23mm cannons. Air brakes in a fully pressurized cockpit became mandatory, since the aircraft were expected to fight at extreme altitudes where dogfighting with just an oxygen mask was physically impossible. The deadline to deliver finished experimental aircraft for testing was set for December 1947. The most practical approach was taken by Alexander Yakovlev, who took a highly simplified approach with his design and submitted his Yak-23 first, but it fell well short of the specified requirements. Soviet military and aviation leadership were still eagerly awaiting the arrival of new fighters from Semyon Lavochkin and Artem Mikoyan. These two prominent designers became the main competitors in the race to create the best jet. Right from the start, both design teams took on the development of new fighters. These were built around the much more powerful and heavier Nene engine. Lavochkin's project was given the designation Project 168. Mikoyan's creation was named the I-310. Both design teams decided to adopt the newest aerodynamic breakthrough of the time, the swept wing. They went with a conventional layout for early jets. They placed the cockpit up front and the engine in the rear. The exhaust was routed straight out the tail. As for firepower, it was meant to be heavy. The plan was to install one 37mm cannon and two 23mm cannons. Furthermore, the engineers tried their best to meet the strict demands of the Air Force. They equipped the aircraft with pressurized cabins, reliable air brakes, and modern ejection seats. Work on Lavochkin's Project 168 progressed smoothly until mid-1947. But suddenly, an unexpected issue cropped up with sourcing the necessary engines. The problem was that the British company Rolls-Royce had developed their Nene engines in two variants. One was a standard model with 4,500 pounds of thrust. The other was an uprated version putting out 5,000 pounds of thrust. However, mass production for both of these versions was only just ramping up. This was especially true for the more powerful one that Lavochkin and Mikoyan were counting on. Because of this, their delivery to the Soviet Union was delayed for several long months. Plus, there was a serious risk that the shipments might be cut off entirely due to growing political tensions. Meanwhile, the other British engines, the Derwent 5s, had already been in large-scale production for quite some time. They had been steadily arriving in the Soviet Union since mid-1947. Finding himself in a tricky situation, Semyon Lavochkin decided on a more conservative approach. By mid-June, he had already greenlit the development of another fighter. This time, it was designed around the more readily available Derwent engine instead of the hard-to-get Nene. The main goal was to maintain the high performance of the new aircraft. This proved to be a wise decision, vindicated when flight testing began successfully in July 1947. This was for the first Soviet experimental fighter with a 35-degree swept wing, known as the La-160. The alternative project was designated Aircraft 174. By September, it received official approval from the ministry. With time running extremely short before the year's end, the engineering team tried to recycle as much work as possible from the previous 168 model. The overall airframe design of the 174 was left practically unchanged. This was relatively straightforward, given that both British engines shared a similar profile. During construction, the designers used existing components and assemblies from its predecessor wherever technical requirements allowed. For both the 174 and 168 fighters, the engineers went with a wing sweep of just over 37 degrees. This allowed them to capitalize on the valuable flight data they had gathered during the La-160's development. On top of that, the designers introduced a completely new empennage. The tail section was also swept back, and the horizontal stabilizer was mounted much higher up on the tail than usual. This configuration proved successful enough to become standard for subsequent Soviet fighter designs over the next few years. Since they opted for a high-wing configuration, the engineers had to use a landing gear setup the Lavochkin Bureau was already familiar with. They decided to retract the wheels directly into the fuselage instead of the wings. It turned out that this workaround provided a distinct aerodynamic advantage. Without the need for wheel wells, the wings were structurally stronger and maintained a perfectly smooth, aerodynamically clean profile. A major challenge and a totally new experience for the team was incorporating hydraulically operated air brakes into the tail section. Developing a reliable, pressurized cockpit for the pilot proved just as difficult, but it was absolutely essential for high-altitude, high-speed flight. The design team successfully integrated both of these complex systems. As for firepower, Aircraft 174 was armed with 3 of the newly developed NR-23 cannons. These were designed under the leadership of prominent weapons engineers Alexander Nudelman and Aaron Richter. Each cannon carried 100 rounds of ammunition. Another standout feature was the ASP-1N automatic gun sight. This was an unlicensed Soviet copy of advanced British technology. This gyro gun sight featured a moving reticle. It automatically calculated the exact lead needed to hit a target by factoring in flight altitude, outside air temperature, and the maneuvering speed of the aircraft. Its only real drawback was its bulky size. However, this was completely offset by its effectiveness. The new ASP-1N sight allowed pilots to deliver accurate fire at distances of up to 800 meters. Meanwhile, older aiming systems were only effective out to about 400 meters. Development of the new Soviet project. 174 aircraft moved surprisingly fast and was successfully completed in December 1947. At the same time, the Mikoyan Design Bureau was not wasting any time either. They had just designed their brand new I-310 fighter. This was an aircraft that would very soon become the MiG-15. This airplane featured an advanced swept wing and was powered by a British Rolls-Royce Nenni engine. However, a problem arose with the supply of the more powerful, uprated version of this engine. Mikoyan found a clever workaround. They simply installed a standard, non-uprated engine in the first prototype. This allowed them to begin flight testing without any unnecessary delays. Meanwhile, back in the factory, they were already busy building a second prototype of the fighter. This aircraft was specifically prepared for the more powerful power plant. Fortunately for Mikoyan's team, all their fears about a disruption in the supply of uprated engines turned out to be unfounded. The British units arrived right on time, so the second MiG-15 prototype did not end up grounded on the tarmac without an engine. Fascinatingly, both prototypes, Project 174 and the IM-310, were finished at almost the exact same time. It was as if they were racing each other. The I-310 fighter was rolled out to the test airfield on Christmas Eve, December 24th. Its competitor, Project 174, arrived exactly a week later on December 31st, 1947. Their maiden flights followed right on each other's heels, too. The I-310 made its historic first flight on December 30th. Meanwhile, Project 174 finally took to the skies just after the New Year holidays on January 8th, 1948. After that came the intense phase of initial flight testing. The chief test pilot for the Lavochkin Design Bureau, the highly experienced Ivan Fedorov, took the controls of the 174. But almost immediately, during those very first flights, a major problem emerged. This issue would end up causing the engineering team major headaches. Under certain flight conditions, the airplane would experience severe buffeting and vibration throughout the entire fuselage. For several months, from January through April 1948, the design team struggled. They needed to figure out what was causing this dangerous vibration. They checked absolutely everything. They reinforced the flight control linkages, adjusted the landing gear doors, double-checked the engine mounts, and even rebuilt the entire fuel system. It took extensive test flights with special recording instrumentation on board before they finally tracked down the root cause. It turned out the problem was structural resonance. The natural vibration frequencies of the horizontal stabilizer were simply matching the aerodynamic vibrations of the fuselage itself. As soon as the engineers stiffened and reinforced the stabilizer, the severe vibration almost completely vanished. After that, the test program progressed much more quickly. At the same time, the factory sped up the construction of the second, improved prototype, designated 174D. This aircraft already incorporated all the necessary design modifications. It was getting ready for the most important phase, which was the Air Force acceptance trials. However, they would never get the chance to finish testing that first prototype. By the late afternoon of May 11th, Ivan Fedorov was making his third flight of the day. This flight was supposed to be the last. His mission was to evaluate the aircraft's stability and handling at altitudes of 8,000 and 4,000 meters. This is roughly 26,000 and 13,000 feet. He leveled off and accelerated at 8,000 meters, reaching an indicated airspeed of roughly 370 knots. Suddenly, the aircraft began to shake violently again. This time, the flutter built up at a rapid rate. The usual recovery methods did not work. To make matters worse, the elevator controls completely locked up. The aircraft became totally uncontrollable. This left the pilot with no choice but to bail out. Earlier, due to the constant vibrations, Fedorov had requested the explosive charge be removed from the ejection seat, fearing it might misfire. As a result, he had to bail out of the plunging jet fighter by climbing over the side of the cockpit, which required significant physical exertion. However, he eventually managed to struggle free and landed safely under his parachute. Beyond the severe flutter, another major issue emerged during these test flights. Moving the control stick or rudder pedals required an immense amount of physical force. It became painfully obvious that flying a high-speed jet on muscle power alone was physically demanding. The designers urgently needed to add hydraulic actuators to the flight controls. So for the upcoming 174 and 168 models, they quickly developed a modern hydraulic flight control system. This would significantly reduce the pilot's workload. Ultimately, the rest of the test program had to be completed using the second prototype, the 174D. Final assembly was finished on June 10, 1948. Just 2 days later, test pilot Ivan Fedorov took the new fighter to the skies. This improved prototype performed much better than its predecessor. The design team managed to completely eliminate the dangerous vibrations. Thanks to the new hydraulic system, the controls were light and responsive. In total, they logged 7 successful test flights on the 174D. By June 22nd, the aircraft was officially ready for military evaluation. But in aviation, timing is everything. The unfortunate 1-month delay caused by the crash of the first prototype played a significant role. This allowed their main competitors to pull ahead. 2 prototypes of the I-310 aircraft, which by then had already received its designation, the MiG-15, reached the evaluation phase exactly 1 month ahead of the 174D. This proved to be a decisive moment in the rivalry between the design teams. The prototype, which would later be known as the LA-174 fighter, was rolled out at the end of June. However, its official evaluation did not begin until August 1, 1948. This delay was caused by the extensive time spent preparing for the traditional aviation parade, as well as ironing out minor discrepancies identified by the military. Andrei Kochakov was assigned by the Military Institute as the chief test pilot for the aircraft. He was one of the most experienced military test pilots in the Soviet Union. The trials themselves lasted nearly 2 months. They ran from August 1st to September 25th, 1948. Military evaluation is always an incredibly demanding test for any aircraft. This was even more true for a brand new fighter the military was eagerly anticipating. It was during this phase that two ambitious projects, the MiG-15 and the La-174, went head-to-head for the very first time. Ultimately, they reflected the complex development history behind both aircraft. The new swept-wing designs yielded flight characteristics previously unseen in the Soviet Union. However, the extremely tight development schedules and the rush by designers to deliver the aircraft to the military had consequences. Both fighters suffered from significant design flaws. When it came to top speed, the MiG-15 and the La-174 were very closely matched. The MiG-15 could hit 562 knots at an altitude of roughly 8,600 feet. Its competitor, the La-174, clocked in at 561 knots at just under 9,800 feet. However, when it came to rate of climb, the MiG-15 took the lead. Thanks to a slightly more powerful engine, its time to climb to 16,400 feet was just 2.3 minutes. Meanwhile, the La-174 took exactly 3 minutes to hit the same mark. On the other hand, the La-174 featured better maneuverability in level flight, along with excellent acceleration and deceleration. This was largely due to its air brakes. These had not yet been installed on the initial MiG-15 test articles, even though they were in the original design. Takeoff and landing performance was also superior on the La-174. Though it was not without its own issues. Due to the increased weight on the wheels, the main landing gear tires blew out frequently. As for maximum range, both fighters successfully exceeded the initial military requirement of 647 nautical miles at an altitude of 32,800 feet. Flying clean without drop tanks, the MiG-15 managed a range of 753 nautical miles. The La-174 covered 702 nautical miles. Thanks to a more refined aerodynamic design, the La-174 outperformed the MiG-15 in stability and handling. This was especially true at extremely high speeds. The MiG-15, however, suffered from some serious problems. Its aileron authority was poor, and the pilot had to fight excessively heavy stick forces. This was largely because the aircraft had not yet been fitted with hydraulic flight controls. Later on, when the MiG-15 entered widespread service, its most notorious issue was an uncommanded wing drop at high speeds. This was caused by a lack of wing rigidity and poor aileron response. Engineers struggled to fix this problem almost right up until the end of the fighter's production run. Of course, the La-174 was not perfect either. At the start of the evaluation, pilots complained about lateral and directional stability issues. They also complained about excessively heavy stick forces. However, the design bureau knew about these deficiencies from earlier factory testing. They were already working on a fix. Right in the middle of the trials, engineers adjusted the wing dihedral. They installed a larger ventral fin. Most importantly, they added the long-awaited hydraulic aileron boosters. These timely upgrades significantly improved the aircraft's handling. Following the modifications, the fighter's flying qualities met almost all of the military's strict requirements. In a dive at an altitude of nearly 26,900 feet, the La-174 reached Mach 0.93. This was a hard limit intentionally set by the chief designer for safety reasons. Even at that speed, the fighter's handling remained completely normal and predictable. In the final test report, the review board specifically highlighted this. The experts noted that the aircraft's longitudinal stability at transonic speeds was its greatest advantage. By comparison, other Soviet aircraft tested up to that point had suffered from instability at much lower speeds. For instance, the MiG-15 began experiencing pitch stability issues as soon as it hit Mach 0.86. Overall, military leadership recognized that the experimental MiG-15 and La-174 fighters were demonstrating excellent performance and tactical capabilities. The aircraft still had some unresolved issues. However, on August 23, 1948, the Soviet government made the decision to put both fighters into full-scale production. Interestingly, this happened right after the MiG-15 completed its initial evaluation. But this was long before the La-174 had finished its own testing. Production of the La-174 was assigned to two major facilities simultaneously. One was the main aircraft plant in Gorky, managed by Surin Agajanov. The other was the Saratov plant under the leadership of Israel Levin. That same government decree ordered the Mikoyan and Lavochkin design bureaus to quickly resolve all the identified technical defects. By November of that year, the updated aircraft were expected to face the evaluation board once again for final acceptance. This was because their serial production was scheduled to kick off at the beginning of 1949. Final acceptance trials for the upgraded La-174 fighter began on December 8, 1948. To meet the military's requirements, engineers had to make a number of significant modifications. A new blown canopy was installed. This significantly improved the pilot's side and downward visibility. On top of that, they needed to increase the radio range to the Air Force standard of 65 nautical miles. To do this, a dedicated antenna mast had to be mounted. They also introduced a system to ensure continuous fuel flow to the engine during negative G maneuvers. This was done along with a number of other minor but crucial refinements. As a result of these modifications, the aircraft's reliability and ease of operation improved noticeably. Granted, this caused a slight drop in top speed. It now maxed out at 550-30 knots at an altitude of 9,840 feet. But this did not detract from the aircraft's overall impression. The La-174 successfully passed all its trials. It was approved as the standard for the upcoming production run. Meanwhile, the aircraft plants were preparing for full-scale production of the MiG-15 and the La-174. Incidentally, the latter would not receive its final designation, the La-15, until April 1949. The main facility in Gorky had started this complex process back in September. This occurred right after receiving the technical drawings for the experimental fighter from the design bureau. However, they ran into a serious problem. The aircraft's initial design was almost entirely unsuited for volume manufacturing. Many of the parts required complex hand-fitting and machining. That approach was quicker and easier when building a single prototype. But for a large production run, it simply was not viable. And the production targets were massive. They intended to build 650 of these fighters at this one plant alone during 1949. Because of this ambitious goal, some historical publications would later mistakenly claim that 650 or 605 production La-15s were built. This was claimed even though the actual number produced was much lower. To salvage the program, the factory engineers had to work against a tight deadline, with the chief designer's blessing, of course. They had to completely redesign many of the aircraft's components and create brand new tooling for them. This effort allowed production to proceed. The first production La-174 fighter rolled off the assembly line in Gorky in late December 1948. Two more followed in January. Production was rushed to meet strict deadlines. The initial design required constant modifications on the assembly line. In the first 3 months of 1949 alone, engineers had to implement over 3,000 modifications and rework 85 key components to resolve numerous manufacturing flaws. Ultimately, this effort streamlined the assembly process, saving 1,200 hours per aircraft. Despite all the early problems, production rates for the La-174 steadily climbed. While the Gorky plant turned out only 5 aircraft in February, that number rose to 13 in March and 21 in April. That same month, a second plant in Saratov assembled its first production fighter. Already by March, military representatives had accepted the first batch of 20 brand new jets. These fighters were immediately sent to a tactical fighter regiment at the Kubinka Air Base. Full-scale operational trials were waiting for them there. It is worth noting that while production ramped up, the Lavochkin Bureau had simultaneously developed 2 more advanced aircraft. The La-168, with an uprated Nene engine, had already clocked 585 knots and nearly reached Mach 1 in a dive. The experimental La-176 went further still, featuring a 45-degree swept wing and becoming the first aircraft in the USSR to break the sound barrier, reaching Mach 1.03 in a dive in late 1948. But every production plant in the country was already at full capacity building the MiG-15 and the La-174, and the question of producing either Lavochkin design was quietly shelved. Despite this setback, the development of new fighters did not stop. In the spring of that same year, efforts were doubled to accelerate work on the MiG-15 and La-174 models. The government officially approved the results of the evaluation, giving the aircraft its final production designation. This became the La-15. The designers were tasked with making a series of technical improvements to the production airframes based on feedback from military evaluation. They were also tasked with creating a two-seat trainer variant of the La-15 for future pilots. To squeeze every ounce of performance out of the hardware, Chief Engine Designer Veniamin Yakovlev was given a special assignment. He was instructed to significantly boost the thrust of the RD-500 engine by incorporating an afterburner. This was expected to further increase the speed of Soviet combat aircraft. But less than 3 weeks later, the situation shifted completely. The catalyst was the new, much more powerful VK-1 engine. It had successfully passed its official bench tests and was accepted into service. Replacing the older RD-45 with this new power plant promised a massive boost in flight characteristics for aircraft designed around it. Almost overnight, the weaker RD-500 engine lost its relevance and was deemed effectively obsolete. As a result, the Soviet government issued a new resolution. This was to completely overhaul fighter production at the major aviation plants. The new plan was to keep just one primary tactical fighter on the assembly line. This was the MiG-15, powered by the brand-new VK-1 engine. By then, Artem Mikoyan and his design bureau were already working on integrating this engine into their production airframes. They also standardized on a single tactical bomber. This was the Il-28, which also utilized the VK-1. The main driver behind this strict standardization was logistics. It was incredibly difficult to operate such a huge variety of completely different piston and jet aircraft simultaneously. The inventory was staggering. It ranged from piston engine Yak-3 and La-7 fighters to early jets like the MiG-15 and La-15. Maintaining this diverse fleet required a massive amount of effort and resources. This was just to keep the Air Force supplied with spare parts and materials. Ultimately, the decision was made to halt La-15 production at the main plant entirely. The plant would then retool for mass production of the re-engined MiG-15. A final decision had not yet been handed down for the other aircraft plants. However, the ultimate fate of the project was clear. The production run of the La-15 was coming to an end. While there was clear logic to the government's reasoning, choosing the MiG-15 over the more capable Lavochkin design sparked debate across the aviation community. When Lavochkin learned of the proposal just before it received final approval, he wrote a personal letter directly to Joseph Stalin arguing the case for the La-168 as the more rational production choice. The very next day, on May 14, 1949, a high-level government meeting officially approved the MiG-15 for sole production. The Air Force Command raised no objections. With that, the door to mass production for Lavochkin's fighters was permanently closed. Even the Aviation Research Institute's collective appeal to Vyacheslav Molotov, urging a proper evaluation of the La-168 with the new VK-1 engine, was completely ignored. Meanwhile, on May 19, 1949, operational trials began for 20 new La-15 jet fighters. Before this new jet arrived, Soviet pilots had been flying Yak-15s. The new aircraft far outperformed its predecessor. It boasted a higher top speed and a significantly better climb rate. It also featured excellent maneuverability, heavier armament, and was much easier to maintain. But the moment these jets entered heavy use in operational squadrons, various design and manufacturing flaws immediately came to light. The main problem with the early production La-15s was the severe unreliability of their Soviet RD-500 engines. When pilots pushed the throttles to combat power between 26,000 and 29,500 feet, the engines would overheat and lose thrust. Furthermore, cracks would start forming in the compressor section. On top of that, the hydraulic system turned out to be highly prone to failure. Its internal valves quickly corroded and clogged with rust, leading to chronic pressure drops. Another weak link was the landing gear, which failed far too often. Not only did the tires wear out prematurely, but the brakes did as well. Interestingly, the engineering team actually knew about the landing gear issue from earlier flight testing. The designers had already drawn up the blueprints for larger, more robust wheels. All that was left was to integrate them into the production line. But the severe engine and hydraulic problems came as a shock because they only surfaced on production aircraft. Beyond these major flaws affecting nearly the entire fleet, there were countless minor issues. On some aircraft, aerodynamic loads would cause the flaps to deploy uncommanded. Cabin pressurization lines would burst, and industrial dust from the air filters would blow straight into the pilots' faces. Overall, the build quality of the production jets was noticeably worse than that of the early prototypes. The reasons behind this were straightforward. The factories had been given an incredibly tight timeline to gear up for mass production. Additionally, Soviet aviation plants at the time simply lacked the experience to manufacture such complex early jets. Plus, the aircraft's design had to be constantly tweaked and modified right on the assembly line. Factory personnel worked extensively to resolve these defects. Modifications were rapidly rolled out on the production line and retrofitted to the operational fleet. However, despite their efforts, the overall unreliability of these early production batches meant that severe in-flight emergencies still occurred. Even before the official operational trials began, a major accident occurred on April 19th. During a practice flight for an upcoming parade, one of the jets caught fire in mid-air. The pilot, Alexander Zotov, became the first person in the Soviet Union to successfully use an ejection seat in an actual emergency. He parachuted safely to the ground and was awarded the Order of the Red Banner. On May 28th, another aircraft crashed due to a mid-flight engine failure, killing the pilot. Then, on July 21st, the regimental commander himself, Alexander Shishkin, was killed during an aerobatic flight. The accident board officially blamed a tail control linkage failure, but by then, subsequent testing had revealed a deeper problem. These new swept wing jets were incredibly unforgiving in a spin. Recovery required precise timing and technique that no pilot had been trained for. The official explanation was disputed, and the true cause was never fully resolved. What mattered politically was who Shishkin had been. He was a close wartime comrade and a favorite pilot of Lieutenant General Vasily Stalin, the influential aviation commander. The general ordered an immediate halt to all military trials of the La-15 and had the remaining airframes transferred to air defense units far from the capital. This was a major setback for the design team, and even though Soviet pilots did eventually fly the La-15 during the traditional Grand Air Parade, the fate of the jet had already been sealed. In August, an official order was issued to permanently shut down the production line. In reality, the defects encountered with the La-15 were typical of early jet aircraft entering initial production. The engineers and factory workers carried out the necessary modifications, which made it possible to rapidly iron out the flaws and bring the reliability of the production fighters up to standard. The specific handling quirks of these new jets, identified during flight testing, were thoroughly documented in the aircraft flight manuals. Thanks to this, the La-15 was operated successfully in tactical squadrons right up until 1954. However, its total production run, which ended in 1949, was modest. Only 235 of these fighters ever rolled off the assembly line. Interestingly enough, the decision to standardize the aircraft fleet bypassed an evolutionary dead end like the Yak-23. Its production began in Tbilisi in August 1949, even after earlier unsuccessful attempts to set up assembly in Novosibirsk. Production continued until March 1951. A total of 313 aircraft were built. The Soviet Union sent most of them to Allied states. Once the final decision was made to halt production of the La-15, the Lavochkin Design Bureau wrapped up its fighter work. The Bureau did develop 2 experimental 2-seat trainer prototypes based on the standard airframe. Both completed flight testing successfully in late 1949 and were later handed over to operational units already flying the combat variant. Ultimately, introducing new swept-wing designs, adopting modern jet engines, pressurized cockpits, and other innovations resulted in a significant modernization of Soviet combat aviation during the late 1940s. If you look at the primary Western production fighters of the era, like the British Meteor and Vampire, or the American F-80 Shooting Star and F-84 Thunderjet, you will notice a common trait. They were all still using outdated straight-wing configurations. Compared to the new second-generation Soviet aircraft, these Western fighters were slower and less maneuverable. The only major exception at the time was the brand new fighter from North American aviation, the F-86 Sabre. It went down in history as the first Western production aircraft to feature a modern swept wing. Its main variants, like the F-86A and F-86E, were powered by reliable General Electric J-47, GE-9 or J-47, GE-13 turbojets. These engines produced around 5,200 pounds of thrust. The Sabre was heavily armed with 650 caliber machine guns. Down at sea level, it could hit an impressive 589 knots. Its rate of climb topped 7,220 feet per minute. Its service ceiling reached 48,300 feet, and it boasted a maximum flight range of 680 nautical miles. This particular American aircraft proved to be a formidable adversary for Soviet MiG-15s. This was especially true during the fierce dogfights over Korea from 1950 to 1953. The La-15 fighters, on the other hand, never saw combat in Korea whatsoever. Semyon Lavochkin's design bureau was among the first in the Soviet Union to develop swept-wing technology. The engineers developed highly capable experimental fighters. These could easily be fitted with various engines from the Rolls-Royce Derwent and Nene to the powerful Klimov VK-1. Despite their technical capabilities, factors outside of engineering and flight performance influenced the outcome. Industrial policy, logistical requirements, and government standardization directives ultimately dictated which aircraft were mass-produced. Because of this necessary standardization, Lavochkin's advanced aircraft never saw widespread mass production, and the MiG-15 became the primary tactical Soviet fighter of the era.